All right, so yesterday we spent an awful lot of time seeing what a radian is, where they come from, and seeing that radians are a truth of circles. We didn't make them up. They created themselves. They are reality, whereas degrees are a man-made thing. They're, we created them. But what we saw was, going to get to the punchline here, a relatively circular, or something that center, and we said we had a radius. And if we took this radius and laid it down around the circle and counted how many times it went around the circle, we found out that it ended like right here after going around 6 times. Let's see if I can make that happen. Picture in front of the scale, obviously, because I'm freehanding this. Whatever, I did what I could. There's one, there's one, there's one there, one there, and one there. And what we saw was we went around this circle 1 radius, 2 radius, 3 radius, 4 radius, 5 radius, 6 radius, and a little more. These 6 and change angles that create an arc that has a length of radius are called radians. And this little bit more happens to be somewhere around 0.28 more radians. More specifically than that, it takes exactly 2 pi of this angle to get around this whole circle, because 2 pi is 6.28 ... So there are exactly 2 pi of this sized angle that fit in this circle, in any circle actually. We call those angles radians. So we say there are 2 pi radian angles in a circle. It takes us 2 pi radian angles to get all the way around the circle. Humans define a circle as 360 degrees. So we define it as 2 pi radians is 360 degrees. This is definition. This is universal truth. How many degrees are in half a circle according to us? 180, yeah. So if you cut 2 pi in half, you get 1 pi. So there are exactly 2 pi radians in a full circle. So there's exactly pi radians in half a circle, meaning it's going to take a little bit more than 3 of these types of angles to get halfway around the circle. I need you to understand that when you say pi radians, you're literally saying a number of angles. This is an angle type, and this is a number of them. It's not a whole number, it's not a pretty number, but it is a truth. It's taking a little bit more than 3 of this type of angle to get halfway across that circle. About 3.14-ish times this size will get you halfway around the circle. Comfortable with that idea? That if there's 2 pi radians in a whole circle, there's 1 pi radians in half a circle. Good with that? So 1 pi radians is defined as 180 degrees. We started yesterday's lesson converting between standard degrees and bearings, degrees, minutes, and seconds, back and forth. That's not incredibly useful unless you're doing some kind of navigation, but what is incredibly useful is knowing how to convert between degrees and radians. And here's why. From here on out, for the rest of the school year and for the rest of all mathematics, if you are ever talking about an angle, it is assumed that angle is in radians, unless you see otherwise. You don't see a degree symbol, that's a number of radians. Degrees are a man-made structure. So we never assume degrees. We assume radians because they're a universal truth. So for the first example, I will write rad, but I don't have to. So rad represents, that's like the unit. It's like saying inches or feet or something like that. It's telling you I had a little bit more than 3 of those radians. I'm only going to write rad for the first example. And from here on out, if I don't write a degree symbol, the assumption is it's radians. Okay, guys? So when you're taking the test, you make sure, if you don't see a degree symbol, to put your calculator in radian mode. I think yesterday you guys saw something not go correct because the calculator's in the wrong mode, or that might have been period 2. Point is, mode matters. Anywho, there's our conversion. And just like we did up here for these conversions, we'll be multiplying by fractions. So that way we could do some dimensional analysis, some unit conversion. It says how many radians are in 90 degrees? Okay, well, I start with 90 degrees. And I need to convert my degrees into a different unit, which means I need my degrees to be on the bottom of this fraction so I can cross cancel the units. Our conversion is 180 degrees in every pi radians. We can cross cancel our units to get 90 pi radians over 180, and then we just reduce our fraction. 90 over 180 is 1/2. So this pi over 2 radians. What do you mean, can you do it on a calculator? You mean reduce the fraction? Oh, and have it convert it to radians? I honestly don't know. I've never tried. That's a good question. Let's see if the calculator can convert that for us. Right now I'm in degree mode. So I'm going to say 90 degrees. And I want to convert that to radians. Well, see, let's change the DRG to radians and hit enter. Yes, actually. But you'll notice it gave a decimal answer. It doesn't say pi over 2. That is pi divided by 2, though. But do you recognize it as pi over 2? If you don't recognize it as pi over 2, even though it can convert it to radians, it won't convert it to fractions of pi. And we need our radians to be in fractions of pi unless we're being told to do otherwise. So even though it can, I mean, you could always say times pi, but that didn't work. Yeah, no. You would have to recognize 1.57-ish as pi over 2. So even though it has the capability, it's not going to return a fraction of pi. Unless you know how to make it do that. And if you figure that out, please let me know so I can teach everybody else. But I don't know how to make it do that. You want to just be able to do the conversions like this. Now, do you need to do conversions by hand every single time? I would hope not, to be honest with you. There should come a point in time where it's obvious that 90 degrees is pi over 2 radians. Let me show you why. Here's that circle again. I'm going to say right here is 0 degrees. All the way around the circle would be 360 degrees, correct? So if I started here and started going that way, if I went 360 degrees, I'd go all the way around. But if I only went halfway around, where would I be? What's half of 360? 180 degrees. But remember, 180 degrees represents pi radians. What is halfway between 0 degrees and 180 degrees? 90 degrees. What's halfway between 0 pi and 1 pi? a half a pi. It would be great if you could start thinking of pi representing 180 degrees. So if you said, okay, 90 is half of 180, oh, 180 is pi radians, 180 degrees is pi radians. Okay, it's pi over 2. Or to see this and go, well, 180 degrees divided by 2, 90 degrees. Be able to convert back and forth very quickly. That is the most efficient way. And I'm going to be honest with you, the faster you can let go of degrees and think in radians, the happier you will be. Degrees are not our friends. They're too big. They grow too fast. I mean, how many degrees is 5 full circles? Time is up. How many radians is 5 full circles? 10 radians, 10 pi radians. See, I just did 5 times 2 pi. But in degrees, I don't know. 5 times 300 is 1500. 5 times 60 is 300. Oh, it's 1800 degrees. How much work that was? And most people would have grabbed a calculator. But if I said, what's 5 times 2 pi? Oh, it's 10 pi. Very simple. Radians are our friends. They keep numbers nice and small. It says how many degrees are in pi over 3 radians? People that understand a shortcut see that this represents 180 degrees divided by 3. It's 180 degrees divided by 3. 60 degrees. So pi over 3 radians is 60 degrees. You don't see the shortcut, no big deal. Remember, if I don't write degrees, it's assumed radians. This time, I'm trying to cancel out radians, which means my pi needs to be on the bottom of the fraction. My degrees need to be on the top. That leaves me 180 degrees divided by 3, which is 60 degrees. No, and there's actually a bunch of them that you will know by heart very quickly. And you'll see which ones very soon. My picture. How many times does 60 go into 180? 3 times. So from here to here is 60 degrees. Here's another 60 degrees. Here's that third 60 degrees. Ignore the pencil line. That's not doing anything. So I go 60, 120, 180. There's a third of 180. There's 2/3 of 180. There's 3/3 of 180. It will become fast. 150 degrees to radians. Because we're trying to convert to radians, I need to be able to cancel degrees. That means I need degrees on the bottom. Go Gators, orange, blue. And we need to reduce our fraction. The biggest number that goes in 150 and 180 is 30. You divide both these by 30. 150 divided by 30 is 5. And 180 divided by 30 is 6. Pi, 1 pi. How many sixths are there in 1? It's not a trick question. How many sixths make 1? 6 of them, right? So there's me cutting it into 2 pieces. And if I want to get 6 total pieces up there, I have to cut each of these two things into thirds. Here's 1/6 of pi, 2/6 of pi, which by the way is pi over 3. Here's 3/6 of pi, which by the way is pi over 2, or 90 degrees. Here's 4/6, which is 2 pi over 3. Here's 5/6. There's 150 degrees, way over there. But what you're doing is splitting your pies, not your full circle, your pies into sixths or into thirds or into halves or into fourths, fifths, ninths, things like that, okay? There you go. Calm, cool, and collected with that. That's how you convert by hand in case you don't quickly see the shortcut. The faster you can work in radians and not degrees, the better your life will be. I'm telling you, trig is much, much easier if you do everything in radians. Nah, I don't want to do what he's saying. I'm just going to convert everything back to degrees, do it all in degrees, and then I'll get my answers in radians afterwards. Holy cow, you must not like yourself. Don't do that. I'm telling you, it's a nightmare. Don't do that. Learn how to work in radians as fast as possible. It's much, much better. So now that we've talked about unit conversion and how many radians are in circles and stuff like that compared to how many degrees are in circles, let's talk about arc length. What is the length known as when you're talking about all the way around the circle? Because an arc is just a piece of a circle. What is the length, quote unquote, of a circle known as? The circumference. And does anybody remember the formula for circumference of a circle? 2 pi r. Did your geometry teacher tell you why the circumference of a circle was 2 pi r? Of course not. And that's not because your geometry teacher was bad. It's because you learned this formula before you learned what a radian was. It's literally telling you if you want to go all the way around this circle, it is going to take you a little bit more than 2 pi. I mean, it's going to take you a little bit more than 6 of your radiuses to get around it. It's going to take you exactly 6.28-ish, or exactly 2 pi of your radiuses to get around the circle. That's where that formula comes from. A piece of the circle is known as an arc. Oh, by the way, the other formula for that is just pi times the diameter, because the radius is half the diameter. Anyway, an arc is a piece of a circle, and we can measure the length of an arc. Now, if you're saying, what is the length of an arc that's created by 1 radian? Oh, the length of the arc is the radius. There it is. But what if it's not 1 radian? What if it's some other number of degrees? Yuck. But radians? Yay! Look how much easier arc length formula is in radians. It's just r theta. Theta is the Greek letter that we use to represent angle measurements. It's the main one. And we use a lot of Greek letters to represent angles. This is the go-to. It's kind of like how in math, your normal variable is x, right? In algebra. But we can use other letters, right? Theta is the Greek letter that we normally use for angles. If we've already used theta, we need to use other things, we will. And I'll show you those along the way. So you can either say theta over 360 times 2 pi r if you're using degrees, because that's what you would have learned in geometry. Or you can just say r theta if you're using radians. If you reduce this, 2 over 360 is 1 over 180. And by the way, there are pi radians in 180 degrees, so that would cancel out and just leave you r theta if you worked in radians. This is our friend. Degrees, boo. Radians, yay. Okay, I'm telling you, radians. Now, something I know you've all wondered, when you were eating that piece of pizza, what was the perimeter of that pizza slice? I know you've all wondered that. All wanted to know. Nobody nodded or said no. Well, you guys are bumps on logs today. Anyway, if for some reason you were really, really nerdy and you wanted to know what the perimeter of a slice of pizza was, you have two options. The yuck option or the yay option. I'm going to go with the yay option. We draw a slice of pizza. Slice of pizza, gorgeous. What we were told is that this slice, my stomach just growled. I'm talking about pizza, get hungry. This slice of pizza has a 60-degree angle down here. Degrees, not radians. And it has a 7-inch radius. The perimeter is just going to be this 7 plus however long the crust is. We need to figure out how long the crust is. Arc length. I want to use the easy arc length formula. I want to use r theta, but that requires my angle to be in radians. So I need to take this 60 degrees, I need to convert it to radians. It would be great if you quickly knew what 60 degrees was in radians, because you quickly recognize that 60 is 1/3 of 180. So it's pi over 3. Just in case you don't know that or don't see that fast, I will convert it by hand like we did on the other side. Since we're trying to cancel degrees, we'll do that. Put the degrees on the bottom. Cross cancel our units. It gets us 60 pi over 180, which does reduce to 1/3 pi, or pi thirds. Pi over 3. Someone in last period asked me, could we write it as 1/3 pi? And I go, well, yeah, you could, but nobody does. It's 100% correct. It's just never written that way. It means the same thing. So our arc length is the radius times the angle in radians, which is just 7 pi over 3. 7 pi over 3 is roughly 7.33. Yeah, it's about 7.33 if you type it on your calculator. On this calculator, you do have to do multiplication. You have to do 7 times pi equals divided by 3 equals. And then you just add. The two sides of the pizza. So this number plus 14. 21.33. A little more than 21 inches to go all the way around that piece of pizza. Aren't you glad you have that knowledge? 7-inch radius of a pizza. That's a 14-inch pizza. What is that, like a medium? Large is typically 16 inches, right? For pizza? I don't know. I don't measure pizza, I eat pizza. It's not too bad though, is it? Hopefully it's easy in radians. The real struggling, stumbling point for students that I've experienced in the past is understanding what this is saying. Understanding that it's saying 1/3 of the way through your 1 pi. Or understanding that that is a little bit more than 1 radian. It's 1.05-ish radians. About 1.05 of this thing is 60 degrees. That's what that says. Because 1 radian is a little bit more than 57 degrees. Running tracks. You guys ever notice when watching the Olympics and any type of track event where they have to go all the way around the track that they always start them in the straight part of the track and they don't start them next to each other? You ever notice that in individual lanes? Yes, no, maybe? You ever wonder why? You've never wondered why? You've never thought like I'd hate to be that person that's all the way at the back? Ah, there it is. Because it's a shorter path around the inside of the track. Because of arc length. Because the inside of the track is literally a smaller arc. And around the edge is the biggest, right? So if you're in one of those races where you have to stay in your lane, you'll notice that they usually try to hug the inside part of their lane because that is the shortest path. The running lanes on a track are 1 meter wide, a little bit more than 3 feet. The inside radius of lane 1 of a track is 33 meters. I don't know if that's true or not, but this is what we had in our book. And the inside radius of the second lane is 34 meters, and that should make sense. Why? Because it's 1 meter long, wider than this one. What we want to know is how much longer is lane 2's inner line than lane 1's inner line around one turn. So imagine a track. Generally looks like this. You got your 2 straightaways, and here's one turn. Here's the other turn. What shape is this one turn? What shape is that? No, that's the whole thing. What shape is one turn? Yes, say it louder. A semicircle. It's half a circle. A track is 2 straight lines and a circle that's been cut in half. So when it says around one turn, it's literally saying half a circle. So let's draw this thing. Picture not drawn scale. And we'll say here's the center of that turn. What we know is that the lanes are 1 meter wide. We know that the inside radius is 33. And we know that the outside radius, well, the inside radius of the outside lane, what a weird thing to say, is 34. And what it wants to know is how much longer is this line than the inside line? Well, you guys told me I'm going around a half a circle, right? Half a circle is how many degrees? Come on, half of a circle is how many degrees? 180 degrees, but I want to use the easy formula for arc length. I want to use radians. So how many radians is half a circle? Pi radians. Because there's 2 pi of those radian angles in the full circle, so there's half of that, or pi radians in the half of a circle. Our theta is pi radians. So the green arc length is r theta, or just 33 pi meters. And the purple arc length, again, r theta, is just 34 meters. It says how much longer is it? If you want to know how much longer something is than something else, what do? You subtract, yeah. So how much longer? You go, well, lane 2 equals 34 pi minus 33 pi, which is 1 pi meters longer. So a little bit more than 3 meters longer if you're running on that line than if you're running on that line. A little more than 3 meters. That's it's probably about 10 feet. I don't know what 3 pi meters is in feet, but I do know that 1 meter is roughly 3 6.1 feet. I know that. So if I said pi meters, it's probably close to 10 feet. If you care about imperial units. There you go. Scary hard? Not bad, right? I hope, especially if you draw a picture. Cool. One more example, and this last example is true dimensional analysis. That's what they call it in physics and chemistry, right? Unit conversion, true unit conversion. We are going to turn a wheel's rate of spin, revolutions per minute, into a speed in miles per hour. A truck has wheels that are 36 inches in diameter. The wheels are rotating at 1 revolution per minute. Excuse me. 630 revolutions per minute. Did I say 1? Yuck. See, 1 revolution. No, we'll do that later. 630 revolutions every 1 minute. We're looking for miles per hour. So we have to convert two things. We're going to have to convert revolutions to miles. We're going to have to convert minutes to hours. One of them is very easy to do. The minutes to hours should be very easy to do. Okay, first thing we know, our truck, the tires have a rate of spin of 630 revolutions per 1 minute. I can convert minutes to hours. How many minutes are in an hour? 60 minutes in an hour, good. And because I was trying to cancel minutes, I had to make sure if it was on the bottom here, it had to be on the top here. If we did the multiplication, we now have revolutions per hour. Easy part is handled. Our job now is to convert our revolutions into miles. We say it again in a slightly different way. Convert a revolution into a distance. So how do I figure out what the distance of a revolution is? There it is. Circumference. Circumference is 1 revolution. And we said at the top of the page that the circumference is 2 pi r or pi d. And our diameter is 36 inches. So our circumference, meaning 1 revolution, is 36 pi inches. Because we know that 1 revolution is 36 pi inches, we can convert these revolutions into inches. And then once we have inches, we can convert that to feet. And once we have feet, we can convert that to miles. And we'll have accomplished our task. I need to cancel revolutions. That means I need revolutions in the bottom of the next fraction. 1 revolution is 36 pi inches. And if you're keeping track of your units, you now have inches per hour. I know something about inches. There's 12 of them in a foot. If you're keeping track of your units, you now have feet per hour. Lastly, you would need to know how many feet are in a mile, and I would put that on the test as given information if I needed you to do this on a test, so you don't need to memorize that there are, it'd be nice if you knew it, but you don't need to memorize that there are 5,280 feet in a mile. It'd be great if you knew that, but you don't need to. I won't make you memorize it. So if you're keeping track of your units, you now have miles per hour. That's what we needed. So we're going to grab a calculator, and I'll grab this one because this ends up being the one that's a pain in the butt. Because you can't type 36 pi on this one, you have to do 36 times pi. So we say 630 times 60 times 36 times pi equals. That's the numerator. There are two numbers in the denominator. So that just means we need to divide this thing twice. Divided by the first denominator equals divided by the second denominator equals about 67.47 miles per hour. Or mi over h. The per means fraction bar. Miles over hours. And that's it. Questions on that? Questions, comments, concerns? Anything I can clear up for you? No? Okay. I hope it went as well as you're making it seem. And that's it.